All right, let's give this a shot. So I took computer assembly, language programming, and computer architecture, and it was based on the NAND2Tetris system, and I found some information lacking. So I was hoping that I can help my fellow students in some of the exercises, maybe give you some information to help you set some ideas up to help you better understand what exactly you're doing when you're using the NAND2Tetris assembly. So without further ado, I'm going to demonstrate this by showing you an example that I had in class. Essentially what we're doing is assigning the numbers -5 through 5 to the registers R1 through R11, and then we're going to go through and, using essentially a for loop, create a absolute value of all these values in R1 through R11. So let's get started with that. So first things first, just quickly looking at our our CPU emulator, we have the D register. So D is our storage location on the CPU, on the ALU. The RAM locations, the things to remember about RAM is that it starts at R0, goes all the way to R15, and those values are special for some reason or another. R16, well, RAM location 16 is actually where variables start to be allocated by the compiler. The user doesn't actually access those, but they can. Usually for the sake of readability, you assign the value at a specific location or at a specific variable, and the compiler will actually keep a tab on that. So let's go and look at that and what that looks like right off the bat. And in a simple example, we're going to take the value at 11, and so what that is doing is initializing the RAM register 11, right? And then we're going to tell it, okay, take what's in the address of 11 and put it in the D register. And remember that D register is like a holding location. And so then we're going to initialize the size variable. We're going to say, hey, grab this. The compiler is going to turn this into at 16. So we're going to initialize the RAM location 16, and it's going to replace that in the code for us, and we'll see that in a moment. And then we're going to take what's in the D register and assign it to M of at size. M is the memory location at size. So let's go and look at this little bit of code here and see what that looks like. So this is the post-compiled version. The Java CPU emulator, when you load a project, actually goes and automatically compiles that part of it. It's going to go and take that at size and turn it into at 16. So let's step through here. So first we're going to initialize at 11. Something that I don't like is that the compiler doesn't show you that it's initializing that at 11 register, and I wish it would. So essentially what happened is we selected that at 11. So now we're going to go and assign the address RAM 11 to the D register, and effectively that just says put in that address into D. Sure enough, there it is. Then we're going to initialize at size, which is essentially 16, the variable at 16. So that's this guy here. And then finally, we're going to take whatever's in D and assign it to the memory location at 16. There we go. That's easy, understandable stuff here. So initialize, the at sign initializes a memory location in RAM. The D register is on the CPU, and we assign the address that we initialized into the D register. And then we go off and we initialize another RAM value, or RAM location, which is 16, because remember, size gets turned into, via the compiler, into a number starting at 16. And so that's where we get that. It initializes that value, and then we say, put whatever's in D into your memory location that's been initialized, which is 16. So that's where the 11 goes in there. Okay, let's look at a few more examples just to get like a different idea of the same concept. So now we need to register the I variable and assign 0 to it. And the way we're going to do that is the same thing. We're going to initialize I. And so this, we're cutting to the chase here because there's an easier way to do this for certain values, and I'll get to that in a moment. Now normally what we might do is say, hey, at 0, initialize the value 0, and then go and do the same D address location thing, and then swap it out and do M equals D. But we're going to do this a little bit better because of reasons which, like I said, I'll explain in just a minute. We're going to go and get rid of this part of the code. We're just going to initialize I, and we're going to assign 0 to it directly. Now the reason that we can do that is based on some information that they give to us for the C registers, for the C commands. And that is that in a comparison, on the right side of that comparison, you can do these actions directly. Like before, there are certain rules to this, and one of them is like you can't assign 11 to M for whatever reason. I don't know what it is, but that's the way it is. So that said, there are these values that we can go and do. And so we can essentially add that, into the comparison. And likewise, these are our appropriate destinations. So in this situation, rather than going through, 4 steps, we're going to simplify it down to 2 and move on. All right, so moving forward, now we're going to start assigning these registers because we need to put those in R1 through R11. So let's start out with the -5. And we can't initialize a memory location at -5, right? So we're just going to go and say at 5. Then we're going to do the same thing, the same little dance. We're going to assign that to the A register, to the D register by the initialized address. And then we're going to go and initialize R1 because we're allowed to do that. R1 is just a placeholder for 1. The compiler actually just transforms R1 into 1, whatever. So now we can't go and just do M equals D because that's not the negative value. What we can do, again, going back to our little table here, we can do -d. All right, let's go ahead and look at these two on the CPU itself. We initialize at I, which, because it is the next value after open register, open memory location after size, it's going to go into 17. So we don't see that happen, but that's essentially what's initialized. And then we're going to say assign 0 to that. Okay, boop, there it is. It's there. You just have to trust that it is there. And I mean, you will see it later. So moving forward, we're going to go and initialize the number 5. So we're going to initialize the RAM value 5. We're going to take that address, the number 5 address, because that's what we initialized, and put it into the D register. Oh, there it is. And then we're going to initialize R1, which you can see the compiler's turned into 1. So it selects that, and it's going to put whatever's in whatever's in D, and take the negative of that and put that in register 1. And there it is. All right. So we're going to skip ahead. We're going to go through and basically just jump ahead. We'll watch the compiler just go through, and I'll comment on different things. So here we can see we're on the number 4. It's doing the same exact process, right? We register R1, and it's going to put -4 into RAM location 2, or R2. And there it goes. 3, same business. There it goes. Now, we do get a little bit more tricky when it comes to... no, actually 2 is the same. My apologies. -2. -1 is different. It's much like the 1, except that we can assign to R5 just the value -1. There it is. So R6 is going to be simple, just like we did before with the 0. We'll put that in there. There it is. R7 will be 1, and it's another direct assign. 2 starts us back to the previous value. So at R8, we're going to see just 2 go in there. There it is. 3, same thing. 4, same thing. 5, same thing. So now we have all our values loaded up. So now we need to go and start doing some other stuff. For the sake of understanding, I'm just going to skip ahead and not write the 4 through -4 through +5 values. Just going to cut and paste those guys right in there, just because that's easy, right? So now our next step is we're going to initialize at ARR, and I'm using this name because that is what all the documentation has for variables. I don't think that ARR is actually necessary, but what it does is it essentially allows us to understand what's going on in the examples that a lot of other sources use, including the book. So this is for the array section. So the first thing we're going to do is we're going to initialize 1, which we already have something in 1, but remember, we're just initializing the RAM location 1. So at 1. The next step is to do the same thing that we've been doing, which is take the address 1 and put it into D. And I know what you're saying, like, Jay, you can go and assign it directly, but we're trying to understand this, right? We want to make this easier. So at ARR is our array name, and so we're going to initialize that. So that's going to go into RAM location 17, I believe. Or is it 18 at this point? Let's look real quick. So 16 is 11, 17 is 0, that was where I went, you'll remember. And so 18 is where ARR is going to. And so we're effectively putting register 1 in there. And then we say AM equals D. So effectively, we just created an array, and that doesn't really make sense. Because essentially, what does that mean, really? What we've done is said, I'm going to initialize a memory location, and I'm going to store the number 1 in there, because 1 is where our array starts at. We've already declared all the numbers in the array, so it's not really the same thing, but it is the same thing. It's just the way we use it. All right. Now we need to get into the thick of our code. We need to declare in a loop. And so we're going to loop through and basically do some things to increment values, do some tests to determine if the value in the array's location is a specific value, and if it is, change that to get the absolute value. So we say, here's our loop. So now let's initialize at I, because we created I. We're going to say whatever's in that location, whatever is in that RAM location, assign that to the D register. Then we're going to initialize at size, and we're going to do a little math to figure out where we're at. We're going to say D equals M minus D. Right? So what that does is the full size that we declared first off is 11, because we have 11 memory locations. We want to take whatever our increment value is and subtract that from size and assign that to D. And then based on that, we're going to declare a jump location called end. And let's go and just to go and make it easier for ourselves, we're going to put that end in there already, right? So that we know we have a location to go to. Oh, excuse me. My bad. A little ahead of myself there. So now we have that conditional we have to create, and we say where D equals 0, which we don't have to actually say when it's basically implied, then jump if it's equal to 0, right? If the value of size minus the increment value, which starts at 0, we initialized it at 0, go and jump to end. So basically we've worked through all our numbers, go and spit us out and go to the end. So then we have to go and do our test. So let's look at that. We're going to initialize I again. We're going to say D equals M. So we're essentially taking whatever is in D, whatever's in I, and putting it into the D register. We're going to initialize that ARR value. And we're going to do something tricky here. We're going to say go to the address based on what's in M plus D. So right at this moment when we're first running through, I is equal to 0. Okay, because we set it up way back here. And it hasn't changed yet. So I equals 0. ARR, which we assigned right here, is equal to 1. So what this tells us is go to the address of M plus D. So in effect, go to R1, or 1. And then take whatever's in that memory location and store it in D. I mean, this is incredibly simple. Like, wrap your head around that. To create an array, we created the variables in the array. Then we created a variable to track where the array starts at. This is opposite and backwards for sure, but part of the reason we're doing that is so that we can understand. You might want to go, and for the sake of simplicity, take that ARR section right here and just move this up before you create the array so that you better understand that this is an array. But really this is only a created array. It's a fabricated array. So now we have whatever is in D, which was in R1, put that in D. And we're going to use that for our jump, which is a negative. So we're saying, hey, this is the location I want you to jump to. We're going to go and create negative, right? So that we have it. But here we're doing a comparison. So again, we need to see in D, it's always a comparison to 0 because, that's what we're only allowed here. There's nothing here that we can effectively check except for D. I mean, hypothetically, we could probably... Can we? No, I think we have to look at what's in D. We can't say whatever is in M, go and base that on. We have to use the D comparison, I believe. Get with your instructor or, test it out yourself and put it in my comments, please. But, so what we need to do is basically see is this value less than or equal to 0. If the value of D is less than or equal to 0, then we're going to jump to negative. And so there's our negative label to jump to. So, that part's effectively done. We need to create the second part of the condition that says, if it's not a negative, what do we do with it? Well, we have to do something because we have to increment I each time we go through, because that's our tracking variable, right? So we're going to call this non-negative. And, this is a new section of code, so we're going to indent. We're going to say, hey, give us our I increment value, and then take whatever is in M and do M plus 1, which, we all seen this before. This is pretty straightforward stuff. And then we're going to say you need to go to a loop, which has already been declared, that loop label, and we're doing a blind jump because we don't need to do a comparison of anything at this point. If we've gotten past the negative value, if we know that whatever was in D is not negative, or in this case, whatever's in the register of the array that we're on, then go and shoot over to negative if it's negative. But if not, then you're in the non-negative loop, and we just need to start the process back up. And so here you can see if it's a non-negative thing, it just jumps, and we start the same process over and over and over again until we get to a negative number, or until the size of the array is down to 0. All right. So now let's look at our negative code, which is going to have a few more steps in it. It's actually going to have these same values. So we could actually just, for the sake of let's get this done, we could just put that in there. Those are the after steps because it needs to do the same exact thing. But we need to initialize I. What's happening here? We need to take whatever's in M and assign it to D. Yeah, we do this all the time. This is our life because we're working with assembly. We need to initialize our array. We need to do A, M plus D, which, we did back here. You'll remember we're essentially taking the address of the array and going into whatever is the initial value to the increment value plus that initial value. Right? We did that here. And then we can say D equals M. Again, this is the non-negative value. And so here's our actual logic. The thing we've been working to is M equals negative D. Negative D. Just like we had to do over here, right? When we were assigning those values, we're taking whatever's in D and we're going to make it negative and assign it back to that location. And that's it. That's done. And so then we just go back to our loop and we jump back to this loop up here. So that's it for the code. I mean, we have to do one last thing, which is create a recursive loop, because that's what they like. That's the standard. We don't want it to run to infinity. We want it to just basically cycle through. And so we just do a blind jump to end. So when all the code has been processed, just sit in a little loop and do your thing. And that's it for the code. Now let's look at what that does and just prove to ourselves that that all worked. We're back here, we're going through the values, and then this is going to be creating the ARR. We'll take up our code and we'll stick it up here, kind of see if we can keep track of it. Here we are at 1. The DA, AR is, they're going to be assigned at 18. There should be a 1 there, is what we want. Yep, there it is. All right, so now we're going to create you'll remember that the compiler doesn't actually deal with those loops, or excuse me, the way that these work is that essentially there's just a line number that we're going to. And so the compiler is actually going to take care of that. And so when we say, hey, go to @loop, it's going to tell us to do something. So let's just see how that looks. That might be a little bit too complicated for this particular thing. But as you can see, we're here at D equals M minus 1. This first run through doesn't do anything, really. It's just basically waiting to get to the negative part. So at this point, we're here. And so now we just said D equals M. And so we put -5 into the D register. And we're saying, hey, if D is less than or equal to 0, go and jump to line 65. And so we should see that. This is our non-negative loop here. We're going to jump to 65. Boop, there it goes. Right? So now it's doing that non-negative code. The first thing it does is essentially do the things to change that into a -1, a -5, excuse me. There it goes. And so, now we're just running through that loop again. So we could just go and boop, 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 watch it go through. And there you go. Interestingly enough, we can see that the 0 register dumps into the negative loop, but it doesn't do anything because the -0 of 0 is 0. Right? And then we also see that the value of the increment is increasing every time we go through. And we should be just about done. There it is. Now we should be in the recursive loop. So I hope that this has helped you understand, what exactly is happening, and how to create arrays, as well as the various registers, what the A, the M, and the D are in C instructions. All right. Please, like and subscribe or something. I guess that's what you do. All right.